All right, so we're getting to the very last topic, boundary value problems, and the final prototype. That's what this is all about. Okay. All right. Yes, that's how we all feel as we get down to the last.
I don't know how to do it.
Oh, now this is like the eigenvalues.
No, I know how to do that part.
What part?
So I just leave my omegas in my iteration matrix. Is that right?
Yeah.
I just like basically plug in what I have in there and just leave omegas everywhere else.
Yeah.
Oh, okay. Maybe I do that.
Okay. And it's incredibly tedious, but
yeah.
It's what?
It's tedious.
Oh, then I'm not. Then this wasn't tedious, so something's wrong.
oh well, I mean, unless you take simplify, cancel out, but. Just because you have to do quadratic formula on things, expressions involving omega to get the eigenvalues.
Oh, I'm not to that part yet.
Oh!
I'm like wondering what that.
Oh, if you're talking about just making the iteration matrices, yeah, there's not much to that.
That's not.
Okay.
Okay.
Yeah, that's the
Can I just plug that into MATLAB?
But that takes numbers, not functions of omega.
Well, I'm not to that part, but I'm talking about just for like the Jacobi and the Seidel one.
Oh, yeah,
Do they have
sure.
Omega?
Yeah.
Okay.
Okay. Boundary value problems. So what I have in my hand are all the notes for the rest of the semester. So as soon as I get through them, we're done. Okay. So what we're looking at is a 2-point boundary value problem. So we're just working in one space dimension. And our general form is y double prime is some function f that depends on x, y, and y prime on some interval ab. So second order ODE. And the thing is, in your first differential equations class, you solved second order ODEs all the time. But those had two initial conditions. Like you specify y of a and y prime of a. But this is a little different. We have boundary conditions this time. So y of a is equal to some value alpha, and y of b is equal to some value beta. Okay, and under appropriate assumptions on f, this problem is guaranteed to have a unique solution. But this is not a class about ODE theory, so I'm not going to talk about that. It's in the notes. Of course, I can say about everything I cover. It's in the notes. All right. So, in this, what's left of the semester, I'm going to cover 3 types of methods. For solving this kind of problem. So first, that I'll focus on today is the shooting method, which takes the boundary value problem and transforms it into an equivalent initial value problem, thereby using the methods we covered at the beginning of the semester for ODEs. And then there's finite difference methods, where we use numerical differentiation formulas for y double prime and y prime, as we covered last semester. And then the third one is a bonus in the coding project, the Rarely-Ritz method. Okay. So, what is the shooting method? So after we get through the lectures on all 3 of these, our last class will be a lab, where I show some code related to these. So the shooting method is, the idea is to solve this boundary value problem. Actually, I should write that. Boundary value problems are abbreviated BVP. by instead solving an initial value problem that has the same ODE. Y double prime is f of x, y, y prime. And then same boundary condition at the left endpoint, y of a is alpha. But for an initial value problem, you do not specify anything happening at x equals b. You're not allowed to. You can only specify conditions at x equals a. So we have y prime of a is equal to some value t. Now, this is y prime, so this is a slope. And the problem is to find the appropriate initial slope t so that once you compute your solution, y of b will equal beta. So if I were to draw what's happening at x equals a and x equals b, so let's suppose we're at alpha. So your solution is going to start out here, and you want your solution to end up here at so y of b equals beta. So you're trying to find the right slope at x equals a. So that slope is t. In other words, you want to find the right trajectory because you're going to aim. So you're trying to find the right angular slope at which your solution should begin, so that once it gets all the way to the other side, it actually hits b. So in other words, you're trying to find. So it's almost like you're trying to aim. That's why they call it a shooting method. You're trying to find the right trajectory, your initial slope, because if you have the same ODE and same initial value alpha, as you change the slope, where your solution ends up is going to be different. So I choose a slope too large, I may overshoot beta, or too flat, I may undershoot beta. But there's some slope that's going to work, and that's what you need to find. It turns out that if this ODE is a linear ODE, it's actually easy to get the right slope. But when it's not linear, then it becomes a lot more challenging, and you may have to fire more than once to hit your target beta.
So is this a constant slope, or is it?
Well, it's best at this point. It's best to think of this as a variable, but you're going to choose or solve for the correct one. Okay. So what I'm going to do is I'm going to first show the linear case. That's far simpler, where you can actually just explicitly solve for this, and then it is a constant, and you can then solve the initial value problem from there. But then the nonlinear case, where you have an equation to solve for the right value of t. Okay. Ah, dang it. Disaster waiting to happen. Sheesh.
So is y prime of a equal to another? Like initial value that we put in there, or did you just do that basically?
Well, okay. The thing is, it's a second initial condition because we're treating it as like an initial value problem. So what we would do is, like, if you think of methods we saw beginning of the semester, like run kind of methods or multi-step methods, we would solve that initial value problem using one of those, and hope that we've chosen the correct slope so that our solution will magically hit beta. But hopefully all this will become clear as I get more detailed. All right. So first, linear case. All right. So what you can do is we can first solve two versions of this initial value problem with specific values. So these initial value problems. Y double prime is the same ODE, but with these initial conditions. Y of A equals alpha, and Y prime of A is 0. And our solution to that problem, we'll call it Y1 of X. Okay. And then the second problem, Y double prime, so same ODE. Y of A equals 0, and Y prime of A is 1. And we'll call that solution Y2. Now, the reason why these help us is because any solution of this ODE for any initial conditions is a linear combination of these. So we can just linearly combine the initial values, and then we can also linearly combine the solutions in the same way. So, then the solution result is called y of x of the original boundary value problem has this form. Y of x is equal to y1 of x plus t times y2 of x, where t is whatever slope we choose. Because if I go ahead and plug in the x equals a and x equals b, so y of a is going to be y1 of a plus t y2 of a. But y1 of a is alpha, and y2 of a is 0. So this y has the, so first boundary condition checks out. Now, let's look at x equals b. So we have y1 of b plus t y2 of b, and that is supposed to equal beta. Okay. So, once we have our solutions, y1 of x and y2 of x, everything in this equation that I've boxed here is known, except for what? T. Well, based on this equation, what's t? I can solve for it.
Beta minus y1 of b over y2.
Wait, where does y1 of beta come from?
Wait,
Where do we get
I'm just plugging in x equals a and x equals b into this.
Yeah, but I get where we got y1 of a equals alpha. Oh, we're just letting it equal beta.
Yeah, because y of x is a solution of our original problem. So we're requiring that this satisfy both our boundary conditions.
So what does y2 of b equal?
Well, the thing is, I can't really write formulas for these, but the point is, we already have y1 of x and y2 of x in full for the entire interval. So I can plug in any x between a and b. after I've done this. So now these values are known.
Okay.
Yeah, but you have to go through all this trouble to solve these initial value problems to get these values. So for real work, computational work is done up here. Okay, so, and the formula, so now I can just rearrange, this is a linear equation, so I can solve this for t. So beta minus y1 of b over y2 of b. Okay. Now, of course, we have to hope that y2 of b is as it's non-zero. But keep in mind, y2 of a is 0. If y2 of b is also 0,
The slope can be 1.
Nothing.
so in fact, actually, yeah, but the whole solution will be 0
Right.
by existence and uniqueness. So it's a non-issue. Because if both boundary values are 0, we know 0 is the solution. Well, actually, the solution of that BVP. Yes, so this is totally not going to happen. Oh. Okay. All right, so the linear case, we only have to fire once, effectively, because, the thing is, once we have this, we don't have to solve again with that slope, because we effectively already did up here.
And how do we find the values of y1 of b and y2 of b? Like by going through that calculation?
Because when you solve these,
Right.
you get the whole solution on the entire interval.
Right.
Yeah.
So you, okay. Okay.
Yeah, as I was actually, I think I told Tiffany that 2 minutes ago. So,
Right.
yeah, because once we have this, we can plug in any x value into y1 or y2. Okay.
So y1 and y2 is just going to be like functions.
Well, you wouldn't have a formula for them because these are numerical solutions, but they would be lists of y values, vectors of y
But
values.
you can put in any value on your x-axis and it's going to give you y.
Yeah. Well, the thing is, you should choose your h, like your spacing, so that x equals b is one of your points, preferably. Otherwise, you have to do some interpolation, and who wants to do that? So, using either some sort of one-step or multi-step method. So this is back to earlier stuff. And you choose h to be b minus a over n, where n is the number of time steps. And I put time in quotes because we're really solving a problem on a spatial domain, x between a and b, but we're treating these as initial value problems, so now it's like your independent variable is followed as time. So you decide up front how many time steps do you want to take, and then you can choose your h. So that way, x equals b is exactly a grid point. So you'll take n time steps altogether, and then you'll have y1 of b and y2 of b. And once you've figured out t, you can go back to here and linearly combine these two vectors of solution values, and that's your solution. Yeah, so solve this IVP, solve this IVP, compute your t, combine, and that's it. So I'm going to label these. I've already labeled these as steps 1 and 2. So I will label this as step 3, the third step. And you'll be able to carry out once you've done these first two things. And then that's your fourth and final step. Because now you have your t value and you can say what the solution is. So this is so in terms of code for shooting method for a linear boundary value problem, bang, 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 done. Nothing to it, right? Okay. Yeah, but the bulk of the computation is this. So any questions about the linear case before we talk about the more difficult nonlinear case? Okay. Now, did I get all that or not? Okay. Because in the nonlinear case, you can't just combine initial values in a linear way and expect to have the solutions combine also. You can't just take a linear combination of solutions and get a solution. So there's a lot more work involved computationally and analytically to find the correct slope. Okay. So, all right, so for nonlinear case, so we need to solve a nonlinear equation y of x equals b, and I'm going to specify the slope t as a parameter, equals, why do I have it equals 0? All right, it should be equal beta. So this is the value at x equals b of the solution of this IVP, same ODE, and then this initial condition, and then this slope. So the idea is, so in other words, the value of y at x equals b now depends in a nonlinear way on this slope. So that's why it doesn't do us any good to solve this kind of problem with a slope equal 1 and then just multiply that by t because of the nonlinearity. And how are we going to solve this nonlinear equation? How do we solve any nonlinear equation?
Quadratic formula by Newton's method.
Yeah, Newton's method or those kind of methods.
Yeah, root finding.
Yeah, general root finding methods. And I'm going to focus on using Newton's method. Although what is, because of the speed of convergence, but what is difficult about Newton's method?
Finding or finding a initial value. Well, I guess we would have
Finding initial guess. Yes, we have it. We can. Well, that is a challenge. But what else is bad about Newton's method? Yeah, it requires a derivative. So we have to figure out how to differentiate. This is our function that we're trying to find a root of, and we have to find a way to differentiate that with respect to basically with respect to the slope, because that is our independent variable. So we can think of this as some function of t in a way, because t is what we're solving for. Okay. All right. Yeah, but we could use any of these methods, but I'll just focus on Newton's method. So back to the final project, Newton's shooting method using newtons is one of the problems. And then there's also secant method, which actually would be somewhat easier because you're not needing the derivative part of this. Okay, so I'm going to let z of x with parameter t, and it's going to be the derivative of y of x with parameter t, t being the initial slope, with respect to t, because this is a derivative that Newton's method requires. Now, what do we know about z? We need to figure out something about z as it relates to y. So I could say z double prime is equal to, all right, well, I need z double prime of, well, basically z double prime of x. So, now the thing is, so this is df dx. Sorry, something seems kind of strange here, but okay. dy dt z. Okay. So this is so this is second derivative with respect to x of partial of y with respect to t. But I can rearrange this. This is the same as derivative with respect to t of y double prime.
Which is that x.
And y double prime is this. So this would be partial of f with respect to x, partial of x with respect to t, plus partial of f with respect to y, partial of y with respect to t, plus partial of f with respect to y prime, treated as an independent variable, times partial of y prime with respect to t. But x does not depend on t at all, so that part is 0. So we have fy, and then dy dt, that's z. And then I have fy prime, and that is going to be z prime. Okay. So, because I can treat this as partial of, with respect to x, of partial of y with respect to t. So basically, again, I can reverse the differentiation operators however I need to, so that I can actually evaluate the expression, because dy dt is z. Okay. All right, so now I have this second order ODE for z. Now, what about boundary conditions? Because now I have another boundary value problem I can solve, or an initial value problem. So, if we look at the, so what I've done here is basically I've differentiated the ODE with respect to t. Now for the initial conditions. On y, we have y of a is equal to alpha. Y prime is equal to t, whatever t is. So now I can differentiate these with respect to t also and get initial conditions for z. So z of at is the derivative of alpha with respect to t, but it's 0 because alpha is a constant. And then z prime of bt, of at, is a derivative of t with respect to t, which is 1. So now I have an initial value problem for y to solve, as the shooting method calls for. But to help me solve that, I also have this initial value problem for z. Okay. So now I can think of this as one big old system of ODEs. I have 2 for y, a second order one for y, and a second order one for z. But all these numerical methods for solving IVPs that we've seen, Rakakoto, number one-step methods, multi-step methods, they work with first order ODEs. Here I have second order ODEs. What do I do about that?
Convert it to 2 first order ODE.
Yeah, so any second order ODE can be written as a system of first order ODEs. Yes. Yes. Yeah. Okay.
Or system.
Yeah, it came up in 605, certainly. Okay. So, all right, so now I'm going to summarize. Here's the system of ODEs I need to solve. And then how we would use that in the context of Newton's method to find the correct slope. And so I'll do this for Newton's method, and then we'll discuss how you do something similar if it was a secant method. Okay. All right. So, and this is to solve at each Newton iteration, so or other root finding method. Okay. So it's y double prime is f of x, y. Well, I'll just say y double prime is equal to f. Okay. Y of a is alpha. Y prime of a is t. And the thing is, for Newton's method, you have to have an initial guess. So that initial guess is what we plugged in here for y prime of a the first time, and you'll keep refining it. And then we also have z double prime. That's equal to f y times z plus f y prime times z prime. Which means you need partial derivatives of f with respect to 2 of its variables, y and y prime, which for certain OD boundary value problems might be a pain, unfortunately. That's one of the drawbacks of Newton's method. And then its initial condition, z of a is 0, and z prime of a is equal to 1. So now we write these as system of first order ODEs. So I'm going to let y1 equal y. Oh, I can use parentheses here. I don't use these in the notes, but just to avoid, because a 1 looks a lot like a prime on the board, even though it would not in the notes. So y1 is just y, y2 is y prime, and then z1 is just z, and z2 is z prime. Okay, so now we have y1 prime is equal to y2, y2 prime is equal to f of x, y1, y2. Okay. Z1 prime is equal to Z2, and Z2 prime is equal to df dy of x, y1, y2 times z1 plus df dy prime of x, y1, y2 times z2, which is z prime. Okay, so now we have a system of 4 first-order ODEs, but these first-order ODEs require initial values. So y1 sub 0, the initial value is going to be alpha. Y2 initial value is going to be t, slope. Z1 initial value is going to be 0, and Z2 initial value is going to be 1. So now this is what you'll solve. You can feed this to code such as Euler forward or Rakakata, something of that nature. Now I can describe an algorithm for Secant method using Newton's method for the root finding part, and we need to choose some time-stepping method to solve these. I'll just throw in Euler's method. It's the simplest one to write out. But you can do something else. Okay. So here's the algorithm. First, you choose initial guess. I'll call it T naught. So superscript 0. And the thing is, Newton's method, as you said, Vivian, earlier, requires a good initial guess. I have no guidance there, so unfortunately. So take your chances.
Hey, on that, the last one, the Z2 prime down there, would it matter if that's Fy, or would we need to make that Fy1?
Oh, wait, right here?
Yeah.
Oh, this is Fy prime. Yeah, so,
But can we leave this Fy prime, or do we need, or would that be of Y2?
oh, I see what you're saying. Because all this means is you're taking your function from your initial boundary value problem. It depends in some way on x, y, y prime. You're treating y prime as an independent variable and differentiating f with respect to that. Yeah. Alternatively, if you think of this now as a function of x, y1, and y2, it would be a partial derivative with respect to y2. So however you want to look at it. Yeah. Okay. So we have our initial guess, and then you choose your time step so that b minus a is h times capital N, which is a number of steps. Okay. And then we have a loop that will keep running until convergence of Newton's method. So the outer loop is for Newton's method. Okay. Now, Newton's method, every step you have to evaluate your function, your f, you evaluate your f prime, then you have your Newton's formula. In this case, evaluating f and f prime is going to be a huge pain. That's where the bulk of the work is. Unlike before, we kind of take that part for granted. So now I'm going to have an inner loop, and for solving this system of ODEs. So I'm going to set my initial values. So like I have over here. So y1 is alpha, y2 is whatever my current slope is, my tk, so initially t0. And then my z1 is 0, my z2 initial values are this 1. Okay, now I do Euler's method. So I have my inner loop handling that. Okay. And I'm taking n steps altogether. So starting from A, and I go A plus H, A plus 2H, and so forth, all the way up to B. Now, first thing I need is an x value. So my x is going to be A plus I times H. Okay. And now I have an x value to plug in to evaluate all these derivatives here. So y1, its time derivative is just y2. So I'll go ahead and put that in here. Now the subscript indicates which time step you're on. All right, this is just straight Euler's method. y2 I plus 1 is y2 I plus h. And now I need this time derivative. So that would be f of xi, y1i, y2i. Okay, so now I've advanced my y values. Now I just have to advance my z values a similar way. So z1, its time derivative is just z2. Dang it. And then my z2 value I need df dy of xi, y1, y2 times z1 I plus fy prime, evaluating the same values, yi1, yi2 times z2 I. So all that's multiplied by h. And that completes an Euler step. So what happens is, after I've done all this, so this whole loop, this is Euler's method. To solve my system of ODEs. Once I've come to the end of that loop, I have my values of my function I'm trying to find a root of, and its derivative. So now I can do my Newton step. So after all this work, the Newton step is actually very simple. So tk plus 1 is equal to tk. Now, what is your Newton's method? Xk plus 1 is equal to xk minus f of xk over f prime of xk. Well, your function you're trying to find the root of is just your y value at the end. So that's y1n, because we go from I equals 0, and then we're going to, the last value we compute is going to be y1n, which corresponds to x equals b. So this minus beta, because we want this to equal beta in the end, divided by the derivative, but that's going to be our z value. And again, at the end, because we want the function we're trying to find the root of, we want its value and its derivative from the solutions of these ODEs at x equals b. So that's why we take the nth one here. So we have to compute all of these just to make it all the way to the end of our interval to get these two values. That's all we care about from all this. But we needed to do all this work to get them. And so now we've updated our slope by our Newton step, and we go back here and use that as our slope the next time around to keep refining our slope until, when I say convergence, it's convergence of tk that we want. And hopefully, because it's Newton's method, we would not need to carry out many iterations, assuming our initial guess is decent.
On for Euler, on Z1 and Y1, why did we use H times Y2 and Z2?
Oh, here? Oh, well, all of this is due to Euler's method. So, because Euler's method for
That was wild.
okay. Sorry, what?
Oh, because the function of T and Y would be Y2.
Yeah. So what you put here is h times these.
Okay.
Yeah. So because this defines your vector value time derivative. Yeah. So it's just this in a vectorized form.
Is that it?
Yeah. That's the whole logarithm. Okay. So that's when you code for shoot newt. In the
And we only use Y1 and Z1?
Oh, down here?
Yeah.
Yeah, because but the thing is, we still need these because notice they all depend on each other.
Yeah.
Yeah. But yeah, that's all we need for a Newton step.
Why do you use those instead of Y2 or Z2?
Oh, because y1 and z1 represent the values of y and our function we want the root of, and its derivative with respect to t, whereas y2 and z2 refer to y prime. From these relationships.
When we do this, can we calculate, can we put in the new value, in some places?
Oh, like right here, for instance.
Yes. Can we put in y1 I plus 1?
Oh, would that work better?
Basically, so it's not Euler's method anymore. It's like almost like an implicit method in a way.
Like Adams-Moulton, right? Like when you
It's kind of like, actually, the closest thing is the Adams-Moulton predictor corrector.
right.
You have to be careful about that sort of thing because you're basically using an unknown ODE method.
And then you can call it the Candace method.
That'd be interesting, though. Yeah, it probably would help actually. Well, it's. Although, the thing that's risky about it is effectively what you're doing is you're saying now this is not f of tn yn, it means something like f of tn plus 1 yn plus 1, kind of. And this is a vector quantity, so it's evaluated partly at time tn, partly at time tn plus 1. So values are inconsistent. Like if I take this y1 value and use it down here, it's not the same as like Jacobi versus Gauss-Seidel. It's not the same. It's not equivalent. So this, if I do that, I'm saying, well, I want to evaluate f of x, y prime, where y comes from one time and y prime comes from another. So to be consistent, we should have the same subscript in both. But because you don't know this yet, You basically made it an implicit method.
Okay.
So, but you probably could fashion that into some sort of predictor corrector type thing, but yeah, it's a can of worms. So, good question, though. Okay. Now, how would this change if we were doing secant method instead of Newton's method? Like, well, what would we not need? Yeah, you don't need z at all because secant method does not require a derivative. So
we just have y1 and y2?
yeah, you would. Now the thing is, yes. So you have this expression. This is kind of like your f of xk, and then also you have to. The thing is, you have to keep your previous y because what happens is, whatever as we go from one iteration, Newton iteration to the next, we overwrite our y's and z's with all this. You have to hang on to this value from a previous iteration.
You need two guesses.
Right.
Like n minus n minus one. Like you need to
Yeah.
compute the first one. You need the second and the well, to compute the second one, you need the first and the third one, right? Like technically, because you need n plus one and n minus one. So
Well,
Could you just do like a
no.
y something equals?
or n plus two and n plus one? Am I thinking different?
no, but each one depends on the previous two.
Right, that's the previous two. Okay.
Yeah, yeah.
Okay.
I'm sorry, you're saying?
Like before you calculate secant, you put under y, you just say y equals secant, yk equals that, so then when we go to the bottom, we do y.
Yeah, just save this somewhere, so you can have it.
Say y equals old y or something.
Yeah.
Yeah,
And
yeah.
then just, use that
Um,
at the bottom.
Yeah, and the thing is, keep in mind, this whole thing is your f value. Don't forget to subtract the beta every time. And then, now, secant method, if we look at the formula for that, okay. Okay. Yeah, I'll go to a new board. Or, didn't really want to, but.
And then do that.
Okay, actually, I still want to keep the algorithm visible. Okay. So, secant method, in general, is xk plus 1 is equal to xk minus f of xk, xk minus xk minus 1 over f of xk minus f of xk minus 1. So, you can think of this, in this case, this is y y1n minus beta, but from the kth iteration. And this is similar, except from the k minus first iteration. So you have to hang on to that y value. Now, what about this part? What should I have there? From the notation of this problem.
Whatever we said our old y. Oh, that's not y.
What?
T.
Yeah, these are t values. tk minus tk minus 1. Because you're trying to compute tk plus 1. So this is, in the notation of our shooting method, yeah. So I'm saying here's the formula that's always written in textbooks for secant method. Here's how you would adapt it to this case. Okay.
But then f of xk. Oh wait, never mind. Okay, I was looking at this numerator.
Oh, yeah.
It's the same thing.
So
It
this
is.
is y n minus one of y1.
For
Is that it?
this?
Yeah.
Well, the thing is, in the algorithm, this keeps being overwritten every time.
Every time.
Yeah, so this is
The one from the before one.
old.
Old y n1 minus. Okay.
Yeah.
We will have another variable for
Yes,
that.
you need another variable,
Right.
but you do not need this one.
Right.
Yeah, and the best part of using secant method is you have no z at all. Don't even do it. So basically you're solving 2 ODEs instead of 4. And you don't have to differentiate f with respect to y or y prime. And actually, I want to show an example of that.
Can you make sure in the shooting Newton's method that your z in isn't 0?
Okay, so that is. Okay, so that's the derivative with respect to t of
Okay, z
y.
in
What that would mean. Okay, once again, the recording got interrupted. I don't think anything was lost. Definitely nothing was lost on the board. But I have an example of a nonlinear ODE. Okay, so y double prime is equal to fxy y prime is equal to y cubed minus y prime. Okay. So here's my boundary value problem. So df dy, you can treat y prime as independent variables. So what is the derivative of this with respect to y?
Now you
minus y prime.
Yeah, minus y prime. So you can think of y prime as a constant that's multiplying y. And then what is the derivative of f with respect to y prime?
Negative y.
Yes. So that is what you would do, and that's what you'd use for your z ODE if you're using Newton's method. Now, in the assignment, the user calling your shooting method function is required to supply f, fy, and fy prime. So my testing script actually computes those for the test problem. This is a test problem I put in there. And you'll see in my test code script, I have these as inline functions. So you don't have to worry about actually computing those derivatives. You're just taking them as given, as input arguments, and you would use them here. Okay. All right. So any questions about shooting method? All right. Unfortunately, I don't have much time. I can do a little more because if I could finish everything actually early, like not need Monday, that'd be great. But things I still have 7 pages of notes to get through. So I'm not sure, maybe a little optimistic, but I'll just
How many did we get through today?
only 2. Yeah. Well, actually, no, 3. Yeah, and plus I can do a little more, so it'll be 3.5. Okay. So that's all I'd say about shooting method. So at least that was covered. We're not behind. But finite difference method, I can at least get started on that.
Oh, that's on that. That's good.
Yes. Yeah, I figured it'd be good to get through that quickly or early to help you guys with that. Okay. So finite difference approach, which is section 14.2. So we're solving the same problem, but now we're no longer treating it as an initial value problem. We're still treating it as an actual boundary value problem. It's using a very different approach. So y double prime is f of x, y, y prime becomes using differentiation formulas from last semester. So for a second derivative, it's a standard difference, yi plus 1 minus 2yi plus yi minus 1 over h squared is equal to f of xi, yi, and then first derivative uses standard difference again, yi plus 1 minus yi minus 1 all over 2h up to n. Now, some notation. By spacing h, it's like a delta x, if you will. That's b minus a over n plus 1. So here's my interval from a to b. So a is x0, and x1, x2, with equal spacing h. And then we have x n plus 1 is equal to b. So that way we have n, because the value of the solution at a and b are known. They come from the boundary conditions. So it's these n values between x1, x2, up to xn. That's for the values at which we want to compute the solution. And each x value is going to be a plus I times h. Okay. All right. And then our y values, yi is an approximation to the solution y at the corresponding x. So that's where all of these come from. Okay. And our boundary conditions, so we have y of a equals alpha, y of b equals beta becomes boundary conditions on our numerical solution. Y sub 0 is alpha, y n plus 1 is equal to beta. Okay. Is there any questions about the setup? Okay, I will talk about the linear case quickly, because that's again a lot easier than nonlinear case. I can be more specific about the kind of ODE we have. Y double prime is equal to P of x, y prime plus Q of x, y plus R of x. Where P, Q, and R are given functions of x, or coefficients, if you will, variable coefficients. So, because it's a linear system, I have, since this depends linearly on y also, you have a system of linear equations solved. A, y is equal to r. And some definitions, y is a column vector that has your unknowns. R comes from this coefficient r of x. So that's r of x1, r of x2, and so on, down to r of xn. Dot, dot, dot. Okay. So that gives us our, actually, shoot. I need to make an exception here. So for these cases, I have boundary terms. So for first one, I have plus, okay, so moves over to the other side. Dang it. Okay. Minus alpha, and I'm going to get 1 over h squared. Okay. Plus 1 over 2h p of x1. I'll explain where it comes from momentarily. But in the other term, I got something similar. So minus beta 1 over h squared minus 1 over 2h p of x n. Okay,
It's just on the first and last one.
only the first and last. Everything else is equal to just an R value. Okay. Now, what's left is the matrix. And I have formulas in the notes, but I'm going to write out the matrix in a more full way so you can more easily see the structure, and then we'll stop. I'll try not to go too much over time. Although some of you are stuck here anyway. So what happens is the entries of our matrix A come from the differentiation rules. Like for the ith equation, the diagonal entries come from your coefficients of yi. The superdiagonal entries come from coefficients of yi plus 1. And then here we have yi minus 1 for the subdiagonal. So if I write out what this is using these numerical differentiation formulas, you have so y plus 1 minus 2yi plus yi minus 1 over h squared. So that is your second derivative. Okay. Minus p times the first derivative. Okay. Minus q of x times y. So I'm moving those terms over to the other side, and that is equal to r. So that's what I have for each equation. Okay. Now, so now for my matrix, so this is A times my y values equals my r values. So r of x1, r of x2, r of xn. Okay. Now, in here, anything multiplying yi goes in the diagonal. So I'm going to have minus 2 over h squared minus q of xi, q of x1 rather. And then keep going down the diagonal. Q of x2, and so forth, all the way down to minus 2 over h squared minus q of x n. All right. Now, what's in the notes is actually all this multiplied by h squared and then negated. That's the only difference. But I'm writing it this way so you can see more readily where it's coming. You can always scale the equations by anything afterwards. Anything that multiplies yi plus 1 goes in the superdiagonal. So 1 over h squared minus p of x1, that's all that goes there. And then we have 1 over h squared minus p of x2, and so forth. Okay. And then anything multiplying yi minus 1 goes on the subdiagonal. So we have 1 over h squared plus p of x, in this case, 2. 1 over h squared plus p of x3. This is over 2h, sorry. Anything p is divided by 2h. And so on. Now, if we look at the first equation, this accounts for yi. This accounts for yi plus 1. Yi minus 1 is y0. It's gone off the edge. So the term that I would have, which would be 1 over h squared plus p of x 1 over 2h times y0 cannot be here. It has to be moved to the other side. So that's why I have subtracted 1 over h squared plus p of x1 over 2h, which thankfully agrees with what I have there, times y0. which is known to be alpha. So that's where that part really comes from. And same thing down below, the term for y I plus 1, that's y n plus 1, again, goes off the edge. So I have to move it to the other side as well. So I have 1 over h squared minus p of x then over 2h times yn plus 1, which is known to be beta. Okay. So that's where those two boundary terms come from. So that's why even if r is 0, we still have the right-hand side from the boundary values. So we have a tridiagonal matrix, because we just keep filling in these in all the way down to the bottom. 1 over h squared minus p of x n minus 1 over 2h. And then down here, 1 over h squared plus p of x n over 2h. Okay, so we just fill in these diagonals. You have a tridiagonal system, which Amber told you about how to solve using Gauss elimination. So everything here is the same as in the notes, except in the notes, negate everything and multiply by h squared, because that gets rid of a lot of pesky fractions. But it doesn't really matter. It's still equivalent. I should mention that, there are conditions on guaranteeing a unique solution based on your spacing h. So solution is guaranteed if q of x is non-negative and h is less than 2 over L, where L is an upper bound on P of x. What this means basically is if you choose h small enough, a solution is guaranteed. In other words, what this does is this makes a diagonally dominant. You may recall from Amber's discussion of iterative methods that, for instance, if you're using a Jacobi method to solve a system, it's guaranteed to converge if A is diagonally dominant. Okay, and I've run so far over time. Sorry about that. So we'll talk about nonlinear finite difference methods on Wednesday, and just keep going from there.